Okay, welcome back. This is P-Dog, starting lecture 5.2, involving the electron arrangement in atoms. Our objective today is students will exhibit the knowledge of the rules governing electron configuration. And so, the electron arrangement in atoms, this is all about how electrons it's arrange themselves around the nucleus of the atom, but they sort of build themselves up from the nucleus in a very particular way. Again, these are called electron configurations, and they represent a distribution of electrons in the energy levels, sublevels, and orbitals to be filled in a given atom. Now, the Aufbau principle, and you kind of have to say it like that, it's got some attitude to it. The Aufbau principle is that electrons are added to the lowest energy orbitals until all electrons have been accounted for. That's the first principle. The second one is the Pauli exclusion principle, and this one has to do with the spin of the electrons. Orbitals can hold a maximum of 2 electrons, and only electrons of opposite spin can occupy the same orbital. But we sort of talked about this with the last lecture, that because electrons have opposite spin to each other, or a pair of electrons that are in the same orbital can become entangled, and they have the opposite spin to each other. And in order for them to occupy the same orbital, they are entangled with this opposite spin, and that's how they can exist in the same orbital. Okay, the third rule is called Hund's rule. Hund. And his rule is this, that electrons occupy equal energy orbitals so that a maximum number of unpaired electrons result. In other words, what happens first is that the electromagnetic repulsion of the electrons is slightly greater than the allowance of the opposite magnetic fields to get them into the same orbital. So, the electrons will repel each other first with the same amount of energy, and so they will distribute themselves into the individual orbitals in a particular sublevel. Okay, and they all are, if they are unpaired, they all have the same spin. So if one of them goes in with a down spin, then all of the ones in that sublevel will also have down spin. And we start representing these using orbital diagrams. Okay, and this is the objective for this one. Students will be able to use an accurately filled orbital diagram to determine the electron configuration for the most common elements. And here's how it works. Okay, the orbital diagrams demonstrate how we fill our orbitals and sublevels. So, in the first energy level, we talked about this before from the earlier page, that the first sublevel, or the first energy level, has one sublevel. It is the S sublevel, and since the S has only one orientation, it can only hold 2 electrons, and those 2 electrons fill up first. And so carbon has a total of 6, and the first 2 are going to be up, and that must fill up before we move on to the next higher energy level, or energy sublevel. Now, 2s has less energy than 2p, and so the 2s must fill up first before we move on to the 2p sublevels. Okay, we've used 2 electrons here, so we have 4 left that we need to use. So this will also have an up electron and a down electron. And remember, these electrons, okay, are the spin. Let's clean that up a little bit. That the electrons are the up electron and the down electron, which is how I'm going to be drawing them from here on out. I'm just drawing the half arrow. These represent spin. Okay, the convention, the the way everybody else does it is we draw up for one arrow and down for the other arrow. It doesn't really matter. We could do left and right, and we could draw them as like this, but we will see the symbol later on in chemistry, and so we don't do that. That's why we use the up and down arrows. Now back to carbon. We've used 4 electrons. We are now left with 2 more that have to get filled in. And according to Hund's rule, electrons occupy equal energy orbitals. These are equal energy orbitals. So that a maximum number of unpaired electrons result. Well, we have 2 electrons. And so they are going to fill up separate sublevels until we run out of electrons. So this will be an up electron and another up electron. And that will count as our full 6. And so the way we would read this is how we fill out the orbital diagram. And the electron configuration for this would be 1s, 2, 2s. And how many electrons are there? 2. This is the number of electrons. And then 2p, 2. And so we use our orbital diagrams to come up with our electron configuration. Iron is the next one. Iron's a bit bigger. Iron has 26 electrons. So iron has 26 electrons, and these are going to follow the same rules. We start with the lowest energy sublevels first, and that will be the 1s. We'll have an up electron and a down electron. Those are pretty big. An up electron and a down electron. Then we move to the next higher energy sublevel, which would be 2s, and this will have an up electron and a down electron. Then we go to the next higher energy sublevel, which would be 2p, and that is an up electron and an up electron and an up electron. Then a down and a down and a down. So that will be filled. And mind you, we have 10 electrons up to this point. We have to get to 26, so we still have another 16 to go. 3s would be the next higher energy sublevel. It's going to get filled up because we have enough electrons to fill that up. Then 3p, and we'll fill that up. All right, and that has created 10 here, and another 8 over here. So now we're down to 8 electrons left. 4s is the next energy sublevel. Those will fill up. And then finally, so we have 6 left. Those 6 will fill into the 3d, and again, according to Hund's rule, they occupy equal energy orbitals so that a maximum number of unpaired result. Well, they're going to distribute each other to, let's erase that 2p here. 1, 2, 3, 4, 5, and we have one more. These are distributed so that they have the most unpaired, but we're going to have one paired electron, and that goes there. And this would be 1s2, 2s2, 2p6, because there's 6 electrons there, 2s2 electrons, 2p6 electrons, 3s2 electrons, 3p6 electrons, 4s2 electrons, and 3d, shoot. 3d, and how many electrons? There are 6 electrons there. This would be the electron configuration. Now, there's something to note here. Notice this 4s fills before 3d. That's because the 4s sublevel happened. There are overlaps in the energy levels. The electron clouds, the shapes of the electron clouds, and the shapes of the orbitals overlap each other, and some extend out further than others. And it so happens that the 4s sublevel requires less energy from the electrons than the 3d sublevel, but not by very much. And so it is only 2 electrons that fill in here before we start filling in the 3d electrons. And so we go to the next page. And this all starts working with our periodic table here, which we'll get to here in a minute. Now, occasionally, this electron overlap occurs where electrons will fill at a higher energy level, skipping other sublevels because of electron repulsion to achieve a more stable structure. That's why we have That's why the 4s sublevel fills before 3d. Okay, which brings us to our electron configurations. In our objective, students will write correct configurations for the most common elements. Here's our notation. It's similar to orbital diagrams, but these are easier, and you don't actually have to draw out all of the arrows. Our notation is this. 2 is the major energy sublevel. This is the same as the rho. Here, let's move this. On the periodic table. The major energy sublevel is the same as the rho on the periodic table. Is the 2. The P, okay, is the sublevel, and it is represented by the block on the periodic table, and I will explain that in a little bit. However, it's which major rectangular portion on the periodic table does that element belong to, or does that particular electron belong to? And then 5 is the number of electrons, so that's P. And then the 5 is how many electrons in that sublevel. Okay. So what we're going to work through are the electron configurations for the first 20 elements. Okay, now, hydrogen is atomic number 1. It has 1 proton and 1 electron. Okay, so its electron configuration is the placement of the electrons. Where do these electrons go? And these go, the first electron goes in the first energy level, first sublevel. Okay, and that is how many, that superscript is how many electrons are in that sublevel. So it'll wind up being a 1s1 is our electron configuration for hydrogen. Well then, helium then would be what? Well, it would be first energy level, first sublevel, but there would be 2 electrons, and so helium would wind up being 1s2. Now, lithium will take us to the second row. If you look at the periodic table, lithium's up there at, lithium is over here. Lithium's right there. And it's going to be 1s2, so 1s1, 1s2, 2s1. And what you'll start finding is that this rectangle over here, all of these in this rectangle are going to be the s sublevels. This block over here that's 6 wide and all the way down to the bottom, this is going to become the p sublevel elements. These in here in the middle are the f sublevel And these down here on the bottom are the D. Okay, so these are the D down here. Now, if we go to lithium, this is going to be 1s2. Beryllium would be, lithium would be 2s1. Beryllium would be 2s2. So 1s, 2, 2s1, 2s2. So let's go back to that. Let's go back to the next page. And this becomes 1s2, 2s1, 1s2, 2s2. And then boron, we start counting across. That's going to be 1s2, 2s2, because that takes us through beryllium and finishes that rectangle. And then we jump across the gap, and we start the P block. And it's the second energy level, okay, with the P, second energy level with the P, with the first electron in the P subblock. Carbon we did earlier is going to be 1s2, 2s2, 2p2. Nitrogen would be 1s2, 2s2, 2p3, and then on across all the way down to 2p6 when we get to neon. Now, an interesting thing happens. Whenever we finish going all the way across the periodic table, we have this p6 happening every single time. And whenever we have an S2 P6 completed for the same energy level, that element is called a noble gas. Alright, but once we get to a noble gas, then we don't have to write all of that again. We have shorthand. And our shorthand becomes taking whatever the noble gas is and using it to help us write the next one. So sodium over at number 11, sodium at number 11 over here is going to be neon 3, neon 3s1. Magnesium would be neon 3s2. Aluminum would be neon 3s2 3p1 for here. Three S1, 3s2, 3s2 3p1, and 3p2, 3p3, 3p4, 3p5, 3p6, and 3po, 3po. No, we don't actually have that. And then we're at argon, which is another noble gas. We've completed our S2P6. So we get to use argon 4s1, and then argon 4s2. And we move on from there. Okay, and notice 4s1 occurs before 3d because of this electron overlap. And so look at the energy level diagrams to see how the energy levels fill. I recognize this is going to be a tough section, so we're going to spend some time on this. So don't get frustrated, and let's be sure to ask questions, and we will go slowly through this to make sure everybody gets it. The homework for this is going to be, okay, so your assignment is going to be this right here. And there you go. It's section review 5.2, so complete that page, those pages in your packet, and do this bookwork right here, the page 150, numbers 50 through 72 problems. That is what's due on the next time I see you, and we'll have a good weekend, and we'll see you guys on Monday.